half-life is the time required to make the initial concentration half. So now what will be the R? It will be R0 by 2, right? So now what we are going to do, this R0 by 2, we are going to substitute in place of this R. For most of the chemical reaction, the rate increases with increase in temperature. So when we increase the temperature, the rate of the reaction also increases. Reactants have higher energy and they are lesser stable, and products which will be formed, it will be always having more stability and less energy. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry. So today I am back with session 4 of the chapter Chemical Kinetics. So in the last session we discussed integrated rate equation for zero order and first order reaction, right, as well as the significance of first order rate equation, that is from first order integrated rate equation, what all are the informations that we can collect regarding that, as well as rate constant for first order gas phase reaction also we discussed. So in today's session we are going to see what is half-life of a reaction and what is a pseudo first order reaction. Thereby we will move on to the next concepts, right? So first let us discuss what is half-life of a reaction. This is also a very important part of the chapter. The half-life of a reaction is the time in which the concentration of a reactant is reduced to 1/2 of its initial concentration. It is represented as T half. So half-life, so from there itself you can say something is becoming half, right? So half-life or half-life of a reaction is defined as the time which is required to reduce the concentration of the reactant to half of its initial concentration. So let's say initial concentration, how do we represent? R0, right? This is the initial concentration. So to make this R0 to R0 by 2, that is half of the initial concentration, how much time is required? That is called as the half-life of a reaction. So I hope it is clear. Now half-life for a zero order reaction. So for a zero order reaction, rate constant is given by the equation K is equal to R0 minus R by T. So this integrated rate equation we have already studied in the last session. So at time T is equal to T half, that is half-life, that is if it is T half, the time is T half, then what will happen? R will be R0 by 2, right? What will be the concentration at that point when the time is becoming half, that is half-life, that is initial concentration becoming half of that, right? So R0 by 2 will be the concentration now at T half, right? So the rate constant at T half, that is instead of R we are going to substitute now R0 by 2. So K will be equal to R0 minus, in place of R we are going to substitute R0 by 2, right? When divided by T half, it's at time T half, right? So instead of T here, we'll put T half here. Now what is going to happen? What it is? K is equal to R0 minus R0 by 2 divided by T half. Right, so we need the T half equation, so I am going to take the T half here. So T half will be equal to, now we are going to take the LCM here, 2R0, that is this into this, 2R0 minus R0 divided by 2 we will get. Right, so now what happens? And divided by K you will have, right? So what is 2R0 minus R0? It is just R0. So you will have one R0 and you have a 2 and K here. So R0 by 2K will be the equation for finding half-life for a zero order reaction. It is different for first order reaction. So this is very important equation to remember. T half is equal to R0 by 2K, where R0 is the initial concentration and K is the rate constant. So it is clear that T half of a zero order reaction is directly proportional to the initial concentration of the reactant and inversely proportional to the rate constant. So from this equation itself we can see T half is directly proportional to the initial concentration of the reactant and it is inversely proportional to the rate constant, right? So this is the half-life of a zero order reaction. Now moving on to the half-life for a first order reaction. So again we are going to start with the integrated rate equation. So for integrated rate equation for a first order reaction is K is equal to 2.303 by T log R0 by R, where R0 is the initial concentration and R is the concentration at time T. Now we are going to consider the time as T half, that is half-life. When T is equal to T half, what happens to this R? Now the concentration will be what? Again R0 by 2. In half-life is the time required to make the initial concentration half. So now what will be the R? It will be R0 by 2, right? So now what we are going to do, this R0 by 2, we are going to substitute in place of this R, right? And the T becomes T half. So how does the equation become now? K is equal to 2.303 by T half log R0. This R0 will remain as it is. This R will become R0 by 2. Right. K is equal to 2.303 by T log of 1 R0 here, and this R becomes R0 by 2. Now we are taking this part to the numerator, means what? This R0 and R0 will get cancelled and this 2 will come to the numerator. So you will get it as K is equal to 2.303 by T, and you will have log 2. The R0s will get cancelled and the 2 will come here. Now what is log 2 value? 0.301. So this 0.301, if you are multiplying with 2.303, you will get 0.693, and you have a divided by K here. That is by the rearrangement of this. So we need the equation of T half, right? So T half will be equal to 2.303 by K. So log 2 is 0.301. So if we multiply these two, we'll get 0.693 by K. That is the equation for T half for a first order reaction. So I hope this is clear. So it can be seen that for a first order reaction, half-life period is constant. Are there any concentration terms in this particular equation or for T half for a first order reaction? No. It is only dependent on the rate constant, not on the initial concentration of the reactant, right? So, initial concentration of the reactant species, it is independent on the initial concentration. For zero order reaction, so the half-life will be directly proportional to the initial concentration, and for first order reaction it is independent of initial concentration. Zero order reaction, it depends on the initial concentration, but for a first order reaction, the T half does not depend upon the initial concentration. So it is important to remember these two equations as well as the derivation for it. Right. Now moving on to what is a pseudo first order reaction. Right. So chemical reactions which are not first order reactions but behave as a first order reaction under suitable conditions are called as a pseudo first order reaction. So from the pseudo itself, it means the word meaning is false. Right. So it is actually not a first order reaction, but under certain conditions it behaves as a first order reaction, right? So a reaction which involves two or more molecules of reactants but the order is one is called a pseudo first order reaction. So let's take an example and understand this. Acid hydrolysis of methyl acetate, that is methyl acetate is undergoing hydrolysis in presence of an acid. So we have the methyl acetate, that is the ester CH3COOCH3, and it is undergoing hydrolysis, that is addition of water in presence of an acid. So what is going to happen? You will get acid and alcohol, right? CH3COOH which is acid and CH3OH which is an alcohol. So now the rate of the reaction, if you are writing, we will get K into what? How do we write the rate of the constant or rate law or rate expression of this particular equation? It is K into molar concentration, that is product of molar concentration of the reactants raised to their appropriate powers, right? So here it is supposed to be K into H2O raised to 1 it should come, right? Because the number of coefficient or the stoichiometric coefficient here is 1. And here you can see CH3COOCH3 raised to 1. But you can see here what is happening. It is H2O raised to the power 0, right? So actually it is supposed to behave as a second order reaction because both of this if we add it should come 2, right? But here what you can see, the concentration of the water is not important here. Even if we take a large amount of water or small amount of water, it doesn't create any changes here. Only the concentration of the ester is of importance here. Hence it is a first order reaction. So what does that mean? It is behaving as a first order reaction but it is actually supposed to be a second order reaction, right? The reason being water is present in large excess and its concentration remains constant throughout the course of the reaction. That is why the concentration of the water does not make an effect here, right? Now inversion of sucrose is also an example. So sucrose is C12H22O11 which is cane sugar, again undergoes hydrolysis in presence of an acid. You will get C6H12O6 and C6H12O6, that is 2 molecules of glucose you will get. Here also you can see the rate expression. Rate is equal to K into molar concentration of the sucrose into molar concentration of water raised to the power 0. Here also you can see because of the same reason the excess of water doesn't create any change in the concentration. So what happens? Only the concentration of the sucrose is of importance here. So you have 1 here, that is why again the order will be 1. Instead of becoming order 2, this is a first order reaction. So these two examples you have to remember. Pseudo order reaction, it's an important definition to remember. Pseudo first order reaction is an important definition to remember with the example, right? Now moving on to the overall things that we have studied till now regarding zero order and first order reaction, right? So the rate law for a zero order reaction, rate will be equal to the rate constant itself, right? And here rate will be equal to K into molar concentration of R. Now you have units for K. For zero order it is mole, liter inverse, second inverse, and for first order it is second inverse. All this we have already discussed, right? Now half-life we have studied in today's session. For zero order it is R0 by 2K, and for first order it is 0.693 by K, right? Here you can remember that it depends upon the initial concentration, and here it does not depend upon the initial concentration. Now integrated rate law in straight line form, that is Y is equal to mx plus C form. So that is A is equal to minus KT plus R0, and here you have for a first order reaction ln A is equal to minus KT plus ln R0. That is in the form Y is equal to mx plus C. Here also it is Y is equal to mx plus C. So here if we draw the graph, here Y axis will be the concentration, X axis will be time, slope will be minus K, and Y intercept will be R0. Here you can see Y axis will be ln A and X axis will be time. Slope will be again minus K, and the Y intercept will be ln R0, right? Now plot for straight line, it will be R versus T as just now I discussed, and here it will be ln R versus time, right? And slope and the Y intercept, from here itself you can see slope will be minus K and Y intercept is R0. Here slope is again minus K, Y intercept is ln R0. So these informations we can gather from the discussions that we have done till now. So I hope the integrated rate equation, the half-life equation, and the concepts regarding the graph is clear for you. Now moving on to the next part, that is temperature dependence of the rate of the reaction. So till now we were discussing how the concentration of the reactant will depend on the rate of the reaction. That is when we studied the rate law expression. Thereby we studied integrated rate equation and half-life of a reaction, right? So now we are going to move on to the temperature dependence on the rate of the reaction. How the temperature affects the rate of the reaction. So the rate of a chemical reaction is significantly affected by a change in temperature. For most of the chemical reaction, the rate increases with increase in temperature. So when we increase the temperature, the rate of the reaction also increases. The ratio of the specific rate constant of a reaction at two different temperatures differing by 10 degrees Celsius is known as temperature coefficient. The rate usually becomes doubled for each 10 degree rise in temperature. So temperature coefficient is written as KT plus T by KT. That is the ratio of difference in temperature between two different temperatures. That is at two different temperatures differing by 10 degrees Celsius. That means if we have a 20 degrees Celsius and 10 degrees Celsius. Here KT is 10 degrees Celsius and KT plus T, that is 20 degrees Celsius. So this ratio is called as the temperature coefficient. So what does that mean is, in every increase in 10 degrees Celsius temperature, what happens? The rate of the reaction will become double, right? So here what you can see, this will be 2, right? That is for every 10 degree rise in temperature, the rate of the reaction becomes double. So that is called as a temperature coefficient. Now moving on to the Arrhenius equation, which is a very, very important equation. This equation is also important. You need to know the terms which is present in this equation, as well as it can come for the numericals as well. According to Arrhenius, reaction rate constant is proportional to e to the power minus Ea by RT at the given temperature T. So according to Arrhenius, he gave an equation which gives the dependence on rate constant with temperature, right? So the equation shows that the rate constant is directly proportional to the e to the power minus Ea by RT. So to remove this proportionality, we introduce a constant, that is K is equal to A into e to the power minus Ea by RT. So this particular equation is called as the Arrhenius equation, which is very important. So here you have K, which is the rate constant, and A is the constant that we are introducing, right? So this is Arrhenius equation. So this A is called as the Arrhenius constant or frequency factor. Then you have minus Ea. Now what is this Ea? Ea is called as the energy of activation or activation energy. Now what is that? We are going to study in the upcoming slides. R is of course universal gas constant, and T is temperature in Kelvin scale, right? So these are the terms which is present here. So this is a very important equation, that is K is equal to A into e to the power minus Ea divided by RT. Okay, so this is the temperature dependence on the rate of the reaction. So this was given by Arrhenius, hence it is called as Arrhenius equation. Right, now what is activation energy? That is the EA which is present here. What is it? It is activation energy. The minimum energy required for the reactants to form activated complex is called as activation energy. So what is going to happen here is reactants are going to collide with each other. It is forming products, right? So there is a minimum energy which the reactants is supposed to possess so that they will undergo collision and it will form an activated complex first. And from this activated complex, the product will be formed. So that minimum energy which is supposed to be present in the reactants, which is being called as the activation energy. So activation energy is equal to threshold energy minus average energy possessed by the reactant molecules. Now, what is threshold energy then? The minimum amount of energy the reactant molecules must possess to form products upon mutual collision is called as threshold energy. So, these reactants are supposed to undergo collisions, right? So, for undergoing these collisions, any reactant molecules cannot undergo collisions. Only that reactant molecules will undergo collisions which are having a specific minimum energy requirement. So, that energy is threshold energy. So, once that energy is there, what will happen? It will collide and it will form an activated complex. So that energy which is required to form the activated complex is called as activation energy, and then further they'll form the products, right? Now we can see an example here, H2 plus I2 giving 2HI. So you can see H2 here which is shown by a single bond here, and you have an I2, I and I formed by a single bond. So now what is going to happen here? You can see an intermediate is formed here. Now this intermediate formed here is called as the activated complex. First, the reactant molecules will collide with each other. It will form an intermediate. So you can see the HH bond and HI bonds are shown by a dotted line here. Now why it is shown by a dotted line here? So here the hydrogen-hydrogen bond is going to break, iodine-iodine bond is going to break, and the hydrogen-iodine bond is going to be formed. Here also this HI bond is going to be formed. So that is the intermediate state wherein breaking of bonds is also happening, wherein the new bonds are also being formed, and finally you will get two molecules of HI. So this is how it is formed. Initially reactants will combine or collide with each other, form the intermediate, and then further the products, right? So you can see here, according to Arrhenius, this reaction can take place only when a molecule of hydrogen and a molecule of iodine collide to form an unstable intermediate. This will collide to form an intermediate. It exists for a very short time and then breaks up to form two molecules of hydrogen iodide. This is a very unstable state. Immediately it will break down and form the products, right? The energy required to form this intermediate called activated complex is known as activation energy. So this two reactants have to collide with each other and form this activated complex or else intermediate. That energy which is required to form this particular activated complex is called as activation energy, which is EA. So here also you can see A. In this position, you have H2 and I2, that is your reactants. So, the reactants must collide, and what is going to happen? It must form an activated complex. So, the energy required by the reactant molecules to form the activated complex is called as activation energy. So, this much difference you can see from the reactants to this level, that energy is called as a activation energy, right? Once the activated complex is formed, now what is going to happen? The products is going to form here. 2HI, you can see the products is formed here. Now you can see here the reactants is placed little above here and the products are shown a little below here. Why is that? Is because reactants have higher energy and they are lesser stable, and products which will be formed, it will be always having more stability and less energy. That is why reactants are placed little above the products. You can see products are here and reactants are here. That is because of this reason. Okay, so this energy which is required to form the activated complex is called as the activation energy. I hope that is clear. Right. Now moving on to the qualitative increase in reaction rate with temperature. So all the molecules in the reacting species do not have the same kinetic energy. There will be n number of reacting species. They all will not possess the same energy. Right. So Boltzmann and Maxwell use statistics to predict the behavior of large number of molecules. According to them, the distribution of kinetic energy may be described by plotting the fraction of molecules, that is Ne by Nt, with a given kinetic energy E versus kinetic energy. Here Ne is the number of molecules with energy E and Nt is the total number of molecules. So if we plot a graph between the fraction of molecules in kinetic energy, you'll get a graph like this, and the highest point of the graph will tell you the most probable kinetic energy. Most probable kinetic energy means the highest number of molecules, what is that kinetic energy possessed by the highest number of molecules. That will be this value you can see here. So that is most probable kinetic energy. Now the peak of the curve corresponds to the most probable kinetic energy, that kinetic energy of maximum fraction of molecules. So this highest peak of this graph will tell you what is the kinetic energy possessed by the highest number of molecules. Right. Now the following figure shows that energy distribution curves at temperature T and T plus 10 such that T plus 10 is greater than T. At temperature T, the fraction of molecules possesses kinetic energy greater than or equal to the activation energy and is capable of making effective collisions. So that you can see here, as the temperature increases from T to T plus 10. Initially the temperature is T. Now 10 degree rises there. So now the temperature will be T plus 10. The fraction of molecules having kinetic energy greater than activation energy also will increase. Initially at the temperature T, there will be some number of molecules or fraction of molecules having activation energy, which is a specific activation energy. Now if we increase the temperature to T plus 10, that means we are increasing the temperature by 10 degrees Celsius, means the fraction of molecules possessing activation energy will be more. Right, we are increasing the temperature, so means more number of molecules will possess the activation energy which is required to form the products. Right, yes, thus effective collision and hence the rate of the reaction will also increase. So what does that mean? If you are increasing the temperature, the fraction of molecules acquiring the activation energy will increase. So more number of molecules is having activation energy which is required, that means more product will be formed, hence the rate of the reaction will also increase. Right, thus an increase in temperature increases the number of effective collisions, resulting in the increase in reaction of the rate of the reaction. Right, so in this graph what you can see, this is fraction of molecules versus kinetic energy. So the first graph that you can see, that is this particular graph, that is the fraction of molecules at temperature T. So you can see only, so this is the fraction of molecules that is shaded in the black, which is having the activation energy at temperature T. Now we are increasing the temperature by 10 degrees Celsius. So this is the graph that you can see. Now what is happening, this much area, that is this much area which is shaded area, the fraction of molecules is having the activation energy. Right, now moving on to the next part, that is how we can calculate the activation energy using various methods. The first method is graphical method. In the Arrhenius equation, the factor e to the power minus Ea by RT corresponds to the fraction of molecules that have kinetic energy that greater than the activation energy. Taking natural logarithm on both sides of the equation, we'll get this equation, that is K is equal to A into e to the power minus Ea by RT is the equation, right? So we are going to take natural logarithm on both sides. So ln of the exponential, if we are taking natural logarithm of the exponential, if we are taking, whatever is on the power will come here as a multiple. So this power will come as minus Ea by RT, the exponential will not remain there. That is e to the power n, if we are taking the logarithm of it, you will get n. Right, I hope it is clear. So that is minus Ea by RT plus ln A. That is for the constant also we are taking the natural logarithm. So now if we are plotting a graph between L and K, that is again we are comparing it with the equation y is equal to mx plus c. So what will be here? Y will be ln K. X will be what? 1 by t. Right, x will be 1 by t because the slope here is Ea by r. I hope it is clear. Right, so it gives a straight line. The slope of this line is equal to the constant minus Ea by r and intercept will be ln A. Hence, by measuring the slope of the line, the activation energy can be calculated. So from this particular equation, that is ln K is equal to minus Ea by RT plus ln A. So if we are comparing it with y is equal to mx plus c, what is that we are going to calculate? Ea, activation energy is the one we are going to calculate using the graphical method. So if we are comparing this, ln K will be my y-axis and the x-axis will be 1 by t, right, 1 by t. This minus Ea by r is your m. So x will be 1 by t. So you will get a straight line and the slope will be minus Ea by r. Slope will be equal to minus Ea by r. So slope into universal gas constant, if you do, you will give the value for activation energy. So this is one method that you can follow to calculate the activation energy using graph, right? The next method is rate constant method, okay? That is, if you are having two different temperatures and you will have two different rate constant. From that also you can calculate the activation energy. So let's see, at temperature T1, ln K1 will be equal to minus EA by RT1 plus ln A1. That is this particular equation that we are using here, ln K is equal to minus EA by RT plus ln A. So here we are going to take it for two temperatures, ln K1 and RT1 it will come, right? Now for the next temperature T2, ln K2 will be equal to minus EA by RT2 plus ln A. Right. Now, since A is constant for a given reaction, K1 and K2 are the values of rate constant at temperature T1 and T2. Subtracting equation 2 from 1. Now, 2 minus 1 we are going to do. So, what you are going to get? ln K2 minus ln K1. Right, this side, that is left hand side, ln K2 minus ln A1 is equal to minus EA by RT2. Right, you have minus EA by RT2 and you will have minus of minus EA by RT1, right? Now what this will be equal to? This minus and minus will become plus. So can I write it as EA by RT1 minus EA by RT2, right? In this way I can write. So that is what is written here, EA by RT1 minus EA by RT2. Now this is in the format ln A minus ln B. What is ln A minus ln B? It is ln A by B. So ln K2 by K1 is equal to, in these two equations, what is the common factor here? EA by R is common. So EA by R is taken outside, 1 by T1 minus 1 by T2. Right. Now if you want it in log terms, what we are going to do? Multiply it by 2.303. So log K2 by K1 is equal to EA by 2.303 R. In place of here, 2.303 will come. 1 by T1 minus 1 by T2 remains as it is. So now what is the final equation? Log K2 by K1 is equal to EA by 2.303 R and we are taking the LCM here. So it will be T2 minus T1 by T1 T2, right? That is 1 by T1 minus 1 by T2. LCM if you are taking, it will be T1 into T2. So this goes here, T2 minus T1 divided by T1 into T2. So that is the equation. So this equation you can use when there are rate constant at two different temperatures. So T2 and T1 you can substitute, K1 and K2 you can substitute, you will get the activation energy value and R value is a constant here. So these are the two methods by which you can calculate activation energy. One is graphical method and another one is using the rate constant. So I hope this is clear. So in the next session we are going to study how the effect of catalyst, that is how the effect of a catalyst is going to affect the rate of the reaction, and then collision theory of chemical reaction. By this we'll come to an end to this chapter. So I hope the concepts that I've covered in this session is clear for you. So that's all for today. Thank you.